This is the short summary for Chapter 7, Part 1. The focus of this chapter was on practical use of monads and semimonads. The title of the chapter is Computations Lifted to a Functor Context, Part 2, because this continues what was happening in Chapter 6, where we used a filterable functor to perform computations using functor blocks. And we reasoned about these computations using properties of the functor block. We will continue this reasoning for monads. The first intuition comes from a computation of nested iteration, which is represented like this, using a functor block. I show how this is transcribed using map and flat map, and I explain what the left arrow does, or the generator arrow. Now, semimonads is not a term that is widespread. It is something I invented in order to describe functors that have a flat map method. They are semimonads because they don't necessarily have a pure method, which is required for monads to have as well as flat map. However, there are many use cases where this method is sufficient and or this method cannot be defined while still satisfying the laws. So in the first part of this chapter, semimonads are the focus. We'll call them monads for short because most of them will be monads as well, but we're only going to be using the flat map operation. The pure operation has no place in this kind of block. There's no syntax for it. You have to use it explicitly. I show how the flat map operation works with lists. And to build intuition, I consider a generic kind of computation with several generators or several left arrows. And the main intuition here is that each generator line, together with everything that follows, generates a new container. And then this is again a new container. Now, because of this, the new container should contain a different number of items than the containers we started with, and yet it must be the container of the same type. Therefore, the set of capacity counts of containers must be closed under multiplication. And this gives us a systematic way of looking at what containers can have this property. So obviously, these are containers that can have any number of elements, containers that can have either 0 or 1 elements, containers that have exactly 1 element, containers that can hold elements in numbers proportional to some number, and that could be the case for some tree-like containers, not necessarily, but this could be. And finally, containers that are undefined with respect to their capacity. It's not obvious how many items they can hold, either infinitely many or we don't even know what it means for a container, for example, with this type signature, to say how many elements it contains. Well, we could say it contains always 1 or it's undefined. So these are what I call non-standard containers. They are not faithfully representing necessarily the idea of holding a certain number of values in them. And yet they're functors, so they're generalized containers in a sense. And we begin with list-like containers. I give examples of using the for yield block and monadic computations to solve these problems. in the code. Now, the containers that can hold 0 or 1 values is another possibility, and these I call pass-fail monads. So the example would be a try in the standard library in Scala that can describe a failure during a computation as well as a computation that succeeds. And I show that this monadic block would fail as long as even one of these computations fails. So in this case, typical pass-fail monads are option, either, and try. And the typical tasks I show with code examples. The next kind of monads is tree-like monads. They're recursively defined and they have a tree shape. So I show examples of binary tree or arbitrarily shaped tree, or also binary tree with binary leaves and arbitrarily shaped tree with leaves. And the shape is described by an arbitrary functor. I show in example code how flat map is defined for these type constructors. I also give an example of a non-monadic tree-like container, which is a binary tree that is always full. It always contains all leaves at some level, which can be defined like this, but this is not a monad. Now I show more visually how flat map works for trees, and I give worked examples of code using tree-like monads. The final type of monads are single value or non-standard monads, where we can just pretend that the container always has exactly one value, and at the same time the container has some kind of context. And this context can be very different. It could be a value of type W, and that's a writer monad, or it could be a read-only context where you read a value of some fixed type E, and so on. There are different contexts. So in this way I introduce the intuition for eval, continuation, and state monads. I also show a systematic derivation of the types for these monads. These are the standard writer, reader, continuation, and state monads. I derive their types systematically from the requirements about what is the type of context that they carry, such as a read a value, or the continuation monad has a context that consists of registering an asynchronous callback for later to be called, and so on. So using the Curry-Howard arithmetic correspondence, I simplify and transform type expressions equivalently, and in this way I systematically derive the type constructors for these four standard monads. So in this way I show that type constructors for these monads are not arbitrarily defined and not guessed in some way, or could be guessed in different ways, but they actually must be of a certain shape. I give exercises that are similar to examples I considered.